So after you have a good understanding about the magnitude and the nature of different forces acting on the system, now we try to combine all the theories together and look at the stability of a system. So when you are performing your first build, you will always encounter one or more than one of the following situations. Your airship might be able to lift, but you cannot stop it. Such a second situation is you can take it off, but it will come back to the ground easily. There are also situations where your system can stay in the air, but it just keeps spinning. You cannot control the movement of the system because you don't know when you should start the propeller and allow it to move in a certain direction. There are also situations that your system will be able to go in a certain direction, but it can never go in a straight line. It will always sway in a certain direction. And the end result is that it's just spinning, just going around and around and around. So these are very, very common in your first build. And the solution of this problem depends on your understanding about the stability of the airship. So the principle of stability is that in equilibrium condition, the system will have a net force equals to 0 because the center of buoyancy and center of gravity will always act on the same line, and they will always cancel out each other in equilibrium condition. But when you rotate the system a little bit, when you give it a small push, maybe it's because of air current, maybe it's because of some unpredicted force acting on the system, it will generate either a restoring or overturning couple. If it generates a restoring couple, that means that it will bring the system back to the original condition, and that is something we call stable equilibrium. The opposite is that one is way away from the equilibrium condition a little bit, it will continue to drift away and become something you cannot control. That is something we call unstable equilibrium. So having the condition of equilibrium is only talking about that particular moment. Stability is actually talking about further step, whether a small disturbance will create issues to the system or not. And stability is something very, very important in design. Before we look at the stability, you need to understand that all the forces will act on the center of gravity, and the buoyancy force will act on the center of buoyancy. The thrust will act on the center of thrust, and the drag will also act on the center of drag. So before we look at the stability, you need to understand what are these centers, and you need to have the ability to predict the position of these centers in your system. Let me give you a very simple example. If you look at your airship as a system with very light air occupying most part of your system, and you have your motherboard, your main body actually located at one end of the system. If you put the motherboard below the helium balloons, you are resulting in a system like this, where the center of gravity, the center of mass, is way lower than the center of buoyancy. So if you are in this kind of situation and you assume that the lift force, the buoyancy force, is equals to the mass of the system, then you are achieving an equilibrium condition according to this picture. If I push it a little bit, if it rotates in the clockwise direction a little bit, you can see that you start to have a moment out. The two forces is still canceling each other, But because they are having a different horizontal position now, so they are generating a rotational moment combined together. And this moment arm together with the two forces will generate a couple, a force that is rotating the system in the counterclockwise direction. And you can see that the counterclockwise movement will bring the system back to the original position. And that's why we call it a restoring couple. So the opposite movement will also apply the same situation. When we rotate in the counterclockwise direction, the restoring moment will always act in the clockwise direction. Meaning that doesn't matter how you move it, it will always come back down to this original position. And this is something called a stable condition. What if you put the mass, the body of your airship on top of the helium balloon? You create a situation like this here. And according to the situation, it is still in equilibrium condition. You can see that the two forces are acting on the same line. They will cancel out each other, and there will be no additional moment acting to the system. So it will stay in this position if you don't move it. But if you give it a small push, and if the system moves a little bit, you can see that now similar situation happen. The horizontal position of the centers now create a moment arm, and the two forces now will turn the whole system in the clockwise direction, which is the same as the movement of the system at this stage. So this will further increase the movement. And when you further increase the movement, the moment arm becomes bigger, and that will generate an even larger force that will turn the whole system more. So the end result is that the whole system will flip. And that is something called unstable. Yes, in the equilibrium condition, it's okay. But once you move it a little bit, it cannot maintain its situation, and it will start to sway away from the original equilibrium situation. And that is something we call unstable. So that's why you can find out in all airship system, the body of it, the mass of the system is always located underneath the helium balloon. We try to make the center of gravity below the center of buoyancy. If you can achieve that in an airship kind of situation, you don't need to worry about the stability in the pitching and rolling direction. They will satisfy the stability condition automatically if you put it in the correct manner. All you need to worry about in the airship situation is only the stability in the yawing direction. Let's give you another example. In the situation of a rocket, if we put all the fuel, all the heavy material towards the end of the rocket, the center of gravity will move down. Imagine that this rocket is now having a thrust, moving it forward. So it is actually cutting the air particle in a vertical direction. If, unfortunately, the rocket actually sway a little bit, maybe due to gust wind, you can see that this projection on the side of the rocket will start to have air particle hitting it. Bear in mind that this rocket is still moving upward at a very high speed. So this air particle hitting the side of the rocket will generate a force. And this force, because the center of gravity is towards the end, the bottom part of the rocket, so the force above the center of gravity is a lot larger than the force below the center of gravity. If we assume that the projected area is similar throughout the whole rocket. So the combined effect is that you will have a larger force turning this rocket further than the restoring moment generated from the bottom part, which is below the center of gravity. And you can see the end result is that this rocket will continue to rotate in the counterclockwise direction and result in an unstable condition. The solution to this problem is that we try to locate all the heavy material towards the front of the rocket and move the center of gravity up. And you can see that if we have a center of gravity towards the tip of the rocket, then the restoring moment will be larger than the overturning moment and result in a stable condition, because the end effect is that the rocket will rotate back to the original position due to the restoring moment. So this is how we can achieve a stable condition. So another solution to achieve stability is that if the center of gravity cannot move towards the tip, one thing we can do is that if we come back to this situation, this is true only when the whole rocket is having a similar thickness. If we put in a fin or a stabilizing fin towards the end of the rocket, then the projected area will be a lot larger, and the air particle will hit on a larger area towards the end, which increase the magnitude of this restoring force. And if the fin is large enough, then this restoring moment will be larger than the overturning moment. And this is a second way to achieve stability, to achieve stable condition in the rocket situation. Some more information about how to achieve a stable system. If we look at the aircraft, so you can see that the two wings are always, for commercial aircraft, is always pointing upward. The tip of the wing will always point upward. The reason is that if this aircraft rotate a little bit, for example, in the clockwise direction, then the wing will now be more horizontal and will have a larger projected area to increase the lift force on the right hand side of the wing. And the left hand side of the wing, when it rotates in clockwise direction, it will become more vertical. So the vertical lift force will be smaller. With a larger lift force on the right hand side, it will create a restoring moment that will restore the aircraft back to the original position. And that is what we call a stable equilibrium condition. The opposite is if the wing tip is pointing downward, then we are having an opposite condition, and it will generate an unstable condition. You will also find this kind of aircraft in jet fighter, because for jet fighter, they want to increase the ability to rotate and the ability to maneuver. So they don't mind to have an unstable condition. They're using the technique of the pilot to control the airship, although it is unstable, but this is what they want in a jet fighter kind of condition. So we are always talking about stable equilibrium condition. There's one exception that is not really following the principle that I just mentioned about. It's talking about ships and vessels. In ship and vessels, unlike the condition in airship, you have the center of buoyancy actually located at the bottom of the ship, and the center of mass is actually located a lot higher than that. So this is similar to the situation where you put the mass on top of the helium balloon. But it will not create unstable situation, The reason is when the ship or vessels actually sway towards one direction, the center of buoyancy, the position of the center of buoyancy will also change, because it's talking about fluid displaced. So the fluid displaced is not the same when compared to the stable condition. So we have more fluid on the right hand side when the ship actually tilts towards the right hand side. This will move the center of buoyancy. The center of buoyancy is no longer in the same position because you now have more water on the right hand side. So this will move the center of buoyancy. If you are according to the original condition, if this water level, if the water distribution will not change, then the center of buoyancy will actually move to the left hand side. But in here, in the vessel situation, because now you have more water towards the right hand side, so the center of buoyancy will not move to the right, but instead it actually moved to the right hand side, will not move to the left hand side, but instead it will move to the right hand side. And the combined effect is that it will still provide a restoring moment. That's why a ship will remain in stable condition, even though the mass is actually, the center of mass is higher than the center of buoyancy. So bear in mind that, as I mentioned, that in a mechanical system, it's always beneficial to achieve stability, to achieve a stable equilibrium condition. But it's not always true. Depends on the purpose. Just like when I mentioned about the jet fighter, there are conditions where we want to make it unstable, or we want to reduce the stability of a system. For example, in a car, okay, it is very stable because of large friction that we actually implement in this mechanical system. But then it becomes very difficult for it to move. You will find the same situation in the airship design. The air resistance, the air drag is so large that it's very difficult for you to maneuver at a high speed. So when you want to go for speed, you need to think about the arrangement of the helium balloon such that you can reduce the skin friction drag first. But in terms of achieving the stability condition, in terms of achieving equilibrium condition, having a system with large friction will always help to stabilize it. But it's not always what you want.